Hey everyone, how's it going? Welcome back. Today we'll be looking at how to merge k-sorted lists. And the question can be to merge k-sorted lists or to merge k-sorted arrays. Doesn't really matter, the approach remains the same, right? So let's first start off with understanding what the question really asks us to do, right? So you'll be given some k number of lists or arrays, and they'll each be sorted on their own, right? So in this example, we have 3 lists, and each of these 3 lists is sorted, right? So we see that each of these lists is in ascending order. And what the question is asking us to do is to merge all of these lists together and return a sorted sequence, right? So we have to merge all of these sorted lists together into one sequence such that the sequence itself is also sorted, right? So yeah, let's see what the sorted sequence will look like once we've merged them together. So we'll end up with a 10 element long sequence which will be sorted in ascending order. It can be ascending order, it can be descending order, depends on the kind of sorting that they've given to you in the initial lists. So if the initial lists were also in descending order, you'd be expected to return a sequence which also was in descending order. But here we are given the lists in ascending order, so we're expected to return back the sequence, the merge sequence in ascending order as well, right? So this is the kind of list that is expected from you to be returned to the column, right? So let's start thinking about how we'll solve this problem. And we won't really be jumping directly into the most optimal approach. We'll slowly start building up the solution from what we already know, and we'll start asking ourselves questions to help make the problem easier and to help solve this problem in a step-by-step manner. Because if you're asked this question in an interview, they don't really expect you to simply throw the right solution at their face right off the bat, right? They want to see your thought process. They want to see how you approach the problem, and they want to see how you kind of tackle some problem that you might have never seen before, right? So we'll kind of follow that kind of approach, right? Right now we have k-sorted lists. Let's start off small. Let's start off with something that we might already know how to do, right? So let's start off by thinking about just 2 lists. What will you do, or how will you merge 2 sorted lists to form one single sorted sequence? Now this might remind you of something that you might have already done. For example, in merge sort, you have 2 sorted lists or 2 sorted arrays, depending on the kind of implementation you're doing. And you're required to merge both of these sorted sequences, right, into one big sequence. So let's see how we do that. So I'll just make the extra lists here disappear, and let's just work with 2 lists for now. So here we are. We have 2 lists with us. Both of them are sorted. And now we are required to merge these lists into one single sequence, which also should be sorted. Now in case of merge sort, if you've done that, if you've not really worked with merge sort before, it's all right. So what we really do in that situation is we maintain 2 iterators, 2 iterating pointers, and we start merging these lists together while comparing each of these elements, right? So the pointers start off at the first element of each of these lists. We know that the first element is smaller, or is the smallest element of the entire list. Or what you can say is, whatever element that you're currently on, that element is definitely smaller than or equal to all the elements that come after it. So if you have 2, you know that 2 is smaller than or equal to all the elements that come after it, and 1 is smaller than equal to all the elements that occur after it in its respective list. So when you have to start merging these lists together, you know that you'll obviously have to start off at the first elements. So let's put an iterating pointer over both of these elements, the first elements of each of these lists. So let's say we have one pointer here and one pointer here. Now the procedure requires you to keep comparing the values of the elements at each of these 2 pointers with each other, and you have to keep selecting the smaller element. What do I mean by the smaller element? I just mean the one with the smaller value, right? So we start off with the first elements here. We have the pointers ready and we start comparing them. Now we have 2 and we have 1. Which of these is the smaller value? It's pretty obvious, we have 1 as the smaller value. So we start off with this. We start off our list by adding 1 to it. We've added 1 to the new list. So we'll advance this pointer that we were maintaining on to the next element in that list, right? So we move this pointer to the next element. And now we've removed 1 from this list. Now we have, again, as earlier, 2 pointers, and we need to compare the values of the elements at those 2 pointers. So we have 2 and we have 4. We select the one with the smaller value, which is definitely 2. So we add 2 to the new list, and then we advance the pointer to the next element. Now we again have 2 elements that we need to compare. One is 3, one is 4. According to our policy, we choose the one with the smaller value. So we choose 3 and add it to the list and advance the pointer to the next element in line. So now the pointer is at 4 and the other list's pointer is also at 4. We have a tie, and it doesn't really matter which one you choose. Let's say we choose the 4 from the first list itself, right? So let's choose this one and we'll add it to the new list that we're creating. So now we have the pointer of the first list at its last element and the pointer of the second list still at 4. So now we compare these two values. We see 4 is smaller, so we add 4 to the new list again. Now we are left with 1 element in each of these lists. So we are at the last element in both of these lists. We compare them. We see that we have 5 and we have 10. Definitely we choose 5 because it's the smaller value. And we increment the pointer to the next element. Now we have completed iterating the first array or the first list, and we are left with 1 element on the last one, on the second list, right? So we just add this element here because there is nothing left to compare. So we simply add this element to the end of the new list that we're creating, and we'll be done. And here you are with the finished list, right? So we just simply merged 2 lists by maintaining 2 pointers, 1 pointer for each list. And we compared the values of the elements at those pointers, and we kept adding the element with the smaller value to our new list, and we kept continuing off to the list until it ended, right? So well, we worked with what we knew till now. We merged 2 lists. Now we have to think about some way to adapt this approach for k lists, right? So here we have the 3 lists back with us. Let's start off by following the same approach as I said, and let's add 3 pointers at the heads of each of these lists. Now, as before, we want to select the smallest element from these lists because we want the final array or the final list to be sorted as well in ascending order. So we see that naturally we'll be selecting 1 as it is the smallest element in these 3 elements that we want to compare. So we'll add it to the new list. As we added 1, we'll advance its pointer to the next element in that list. Right. Now we again have 3 elements that we want to compare. We have 2, we have 4, and we have 5, right? So we have these 3 elements that we want to compare, and we want to again choose the smallest element from these 3 elements that we have our pointers at, right? So again, by analyzing this, we see that 2 is the smallest value, and we add 2 here, and we increment the pointer for 2 that we had here to the next element of the list. So we have the pointer at 3 now. Now we have again 3 values that we want to compare, and we want to choose the smallest one. We have 3, we have 4, and we have 5. So we'll choose 3 as that is again the smallest value, and we'll add it to the new list. And we'll increment the pointer to point to the next element in that respective list. So we'll increment this pointer to point to the next element. Right. Now we again have a tie here because we want to select the smallest element. We have 4, we have 4, we have 5. So we can choose either one. Let's say we choose this 4 that we have right here. So we'll add this to the new list and increment the pointer to the next element. Now we have 3 elements to be compared once again. We have 4, 10, and 5. And we'll simply bring up 4 and add it to the new list. And we'll increment this pointer to the next element. Now we have again 3 elements to be compared, 5, 10, and 5. We have a tie. So let's say we add the 5 from the last list to the list, to the new list that we're creating. And we advance this pointer that we have to the next element of this list. Now again, we compare these 3 values. We see 5 is the smallest one, and we'll add it to the new list. And we advance the pointer now. And we see that this pointer ends up at the null node. Hence, we have completely iterated through the first list. So we won't be needing it for further comparisons. So let's just focus on the 2 lists that are remaining with us now, right? Okay, so we see that we have 10 and we have 6. The smaller value is 6, so we'll add it to the list and we'll advance the pointer further. Now we see we have 2 values which are 10 and 11. So we'll first add the 10, then we'll add the 11, and then we'll be done with our iterations. So I won't follow all the steps, I'll just add them to the list because you probably know how we are proceeding here. Alright, so this approach seems to work for k-lists as well. It worked for toList and it seems to work for k-lists as well. Alright, so where's the challenge then? When you start to program this out, you'll realize that you face one very big technical hurdle while trying to implement this out. And where is that? Alright, so let's go back to starting this algorithm with k-lists. You had your 3 pointers. They were pointing at 3 elements. We simply chose the smallest one that we could see and we just added it to the new list. Now, how do you actually choose the smallest element? Right now we just have 3 elements and we can actually see them from our eyes. So we just know that, okay, this is the smallest one and you chose it here. But how will you implement that in code, right? And when you have multiple number of pointers, how do you compare all of them and how do you find the smallest one from all of those pointers? Let's say you have 1,000 pointers because you have 1,000 lists. So how will you choose the smallest element at each of those pointers? Let's start thinking about the kinds of data structures that we've learned about. We know that there is a data structure called a heap. In particular, we have a data structure called a min heap. A min heap always allows you O of 1 access to the smallest item in a group of items that you have. So let's say we have a group of nodes from all of these lists. Let's say we have a group of these 3 nodes. If we want the smallest element, we just have to ask the min heap. We'll just say that, okay, min heap, just give me the smallest element that you have. It'll magically just give us that element and it will just do that in O of 1 time, right? So that is very efficient and it's a really easy way to store all these elements. You just encounter an element and you push that into the heap. Then you ask the heap for the smallest element that it has and it returns that smallest element back to you. So let's see how we'll work with that. I'll just add a heap to the workspace. So here we have our heap on the right hand side and we'll keep adding all the elements that we point to this heap, right? So currently we are pointing to 2, 1 and 5. Let's just add them to the heap. Alright, so we've added these elements to the heap. We've added the 3 elements that we are pointing to into the heap. Before we proceed further, I just want to make some points very, very clear, like the special properties that a heap allows us to have. The first one being constant time access to the smallest element. And the second one being log of k insertions and log of k deletions, where k is the number of elements present in the heap, right? So at max, we'll always have k number of elements in the heap because we have k pointers and we only maintain those elements that we are pointing to inside the heap, right? So right now we have 1, we have 2 and we have 5, right? So let's ask the heap to return to us the smallest value that it contains. It does that in constant time and it returns us 1. So we add 1 to our new list, right? So we add 1 to our new list. We remove it from the heap and we add the next element after 1 into the heap. So we add 4 here. Now, we simply ask the heap, alright, give me the smallest value that you have right now. So it magically just returns us the smallest value that it contains, which is 2, and we add that value to the new list. Now once we've added that, we remove this value from the heap and insert the next element that comes after that current node that we just removed. So we just removed 2, so we'll add the next element, that is 3. And if you're wondering how we just add the next element, we always know that we are using linked lists here. So the next element is like a constant time access, right? So you always have constant time access to the next element. You just have to access the next pointer for that node and you'll simply have access to that element, right? So now we have 3, 4 and 5. We simply ask for the smallest element and then we get 3. So we take the 3, add it to the new list and we remove it from the heap and we add the next element after the 3. So we see that we just removed 3 from the heap. The next element is 4. So we add the 4 into the heap. Again, we ask the heap for the smallest value that it contains. It returns to us 4. It can be either of these 4s. We don't care about that. Let's say it returns to us this 4 here, right? So we add this 4 to the new list and we add the next element after the 4 into the heap. So we remove it from here. We add it to the new list and we add the next element after that 4 into the heap. We keep continuing this procedure further. So we see 4, 5, 10. We get the smallest element, which is 4. We add it to the list. We remove it from the heap and add the next element in line in that particular list, which is 5. So we add 5 to the heap. We again poll for the smallest element that is present here. We get 5. We add it to the new list. We remove it from the heap and we add the next element that it is pointing to. So we have 6 because we removed this 5 from this list. So the next pointer points to 6. So we add that to the heap. We again ask for the smallest element that is present in this heap, which is 5. So we add 5 to the new list. We remove it from the heap and add the next element that it is pointing to. But wait, we just realized that there is no other element after 5 in this list, right? So we don't add anything and we just ignore this list further on. And we just work with these two elements here. Now, we see which is the smallest value present in this heap right now. It is 6. So we remove it from the heap and add it to the new list. Now we take the next pointer of the 6. We see that it's 11 and we add it to the heap. Now we ask the heap that, okay, give me the smallest element that you have. It gives us 10. We remove it from the heap, add it to the new list, and we see the next pointer of 10 points to a null node. Hence we won't add that. We'll just stop checking this list now, and we see that the only element that we have in our heap now is 11, right? So we just take this element, we ask the heap for its smallest element. It only has one element, it returns 11 to us. So we add that to the new list, and we empty the heap here. And this is the final list that you end up with. We knew how to merge two sorted lists. We adapted that algorithm to k-lists. We faced the difficulty. We looked back onto our knowledge of data structures and just thought about how we can get over that difficulty and work through the problem further. We realized that the difficulty that we were facing, which was to find the smallest element from, let's say, k elements, was easily solved by using a heap. So we adapted a heap into our process. And we simply follow the same procedure as we did in two lists for k lists as well. And we end up with a pretty optimal solution right here. So this is how we will be solving this. So let's jump into the code editor and see how we'll implement this in code. Alright, so here we are in LeetCode. So let's begin coding the solution out. Right, the first thing that we'll do is check if this lists vector is empty. So if that is the case, I'll simply return back a null pointer. Next, we need to define a heap that will store our k nodes, right? So let's just define a priority queue, because priority queue is how heaps are implemented in C++. They'll contain list nodes, so I'll just define that type here, and I'll just name this PQ. Alright, so this is a priority queue. This will by default be a max heap, and but if you try and work with this priority queue, you'll see that you'll face some errors, and that is mainly because you'll have to define a custom comparator for this. Because list nodes are not a default type, and the compiler will not know how to compare two kinds of list nodes. So you'll need to do that on your own. So let's just define a comparator, which will be a lambda. So you define lambda in this manner. You can probably read up more on them on Google. So it's pretty easy to define lambdas actually. So you can just look that up. So yeah, I'll be passing in two elements which I want to compare. One of them will be called A and one of them will be called B. Now I'm passing them as auto ampersand, auto just for the automatic type inference, and ampersand for passing them by reference so that I don't make useless copies. Right, so now we need to return a comparison. The kind of heap that we want to build is a min heap. And the funny thing about heaps in C++ is that the kind of comparison that you define for a heap is usually the opposite kind of comparison to the kind of heap that you want. So if you want a min heap, you need to define a greater than comparison. If you want a max heap, you have to define a less than comparison. I kind of found that out like while experimenting with all of this stuff. And I later realized that this is because of how these heaps are represented in memory in the form of vectors. So you can read up about that if you want. But yeah, because we want to define a min heap, we return back a greater than comparison. So I return a val greater than b val, right? So this is a greater than comparison, which will be governing the kind of sort that a heap will have. Next, we need to add this type or incorporate this comparator into a heap, right? So to do that, first of all, you need to define the kind of container that you'll use. I'll use a list node vector, which will contain list node pointer. So I add that star here. Next, I need to tell it the kind of type of the type of my comparator. And we can't really judge the type of our lambdas here. So we'll need to leave that work to C++. And C++ defines a very handy function called decal type. So you write that like this. And you pass in the function or the lambda that you want to define the type of. So I'll just pass in comp here. This also reminds me that I need to add a semicolon here. Yeah. Next, you have to pass the comparator to the constructor of this priority queue. So you'll pass comp here beside the name. All right. So that was pretty implementation heavy, but yeah, this is how you will define the priority queue. Next, you want to add the starting nodes of each of these lists or these linked lists inside the lists vector into the heap. So you'll be inserting all those k nodes into the heap. So we'll just use an automatic iterator. So I'll just do a for auto, let's say node amongst the lists. So this will simply iterate over all the linked list nodes, and this node will basically contain the starting node of all of those lists. So if that node exists, if that node is not null, I will push that into the priority queue, right? So I'll do pq.push node. Yeah, so that is it. Next, we want to start working with the actual algorithm. We need to start building the new list. So let's just define a dummy head for the new list. So let's just call that list node dummy. We'll initialize it with some random value, doesn't matter which value. We'll also define a tail pointer, which will keep track of the tail of our new list. So let's just call it list node star tail. Note that this is a pointer, so I'm adding a star here, equal to ampersand dummy, because we want to initialize it at the same location as the dummy list node. Right, so now we will start working with the heap, and we'll keep polling the smallest element out of the heap until the heap becomes empty. So we'll write a while loop now, and we'll keep going through that while loop until the heap becomes empty. So I'll just write while not heap, pq dot empty. While the priority queue or the heap is not empty, we'll keep going. Now we need to poll the smallest element from that heap that we have, right? So we'll get the smallest element using the top top member function of the heap. So let's just store it in some variable called temp, and we'll say auto temp equal to pq.top. So this will give us the smallest element, because the smallest element is always at the top of the heap. We'll pop that element out. Next, we will add it to the end of our new list. So we'll just do tail next, because tail is the last pointer of our current list. So we'll do tail next equal to temp. We'll move it to the new last element, which will be the element that you added just now, the latest element. So we'll just do tail equal to tail next. Right. Now you need to check that do any other nodes exist in the list after the current node that you just popped, right? So for example, you just popped one node from the heap, you added it to the new list. Now you need to check, do any other nodes do any other nodes exist after this node in the original list that we were picking these nodes from? If there are more nodes after this, you need to check that, and you need to add the following node into the heap, just as we discussed in the algorithm, right? So we'll just check if the next node exists. If it doesn't, it means that we are at the end of that list, that particular linked list. So we'll just do if temp next. This will just check if the next pointer is null, or if it does exist. If it exists, we'll push that into the priority queue. So pq.push temp next, and yeah, that should be it. In the end, you just need to close off the new list that you just made. So make the next pointer of your tail equal to null, so that we don't have any loops. I'll just write tail next equal to null ptr, and we'll just return back the next pointer of the dummy node that we had defined, right? The dummy node just serves the purpose of keeping track of the head of the new list. So we'll just return dummy.next. So I'll try and run this. Hopefully this runs. All right, so it does get accepted. Let's submit this. And well, 24 milliseconds, faster than 94.18%. All right, so this is how you solve this problem. I hope you understood what I tried to say in this video, right? And yeah, by the way, there is another implementation using a map. I have that implementation on my repository. I'll be linking it down below, so be sure to check that out. That implementation kind of runs faster than this heap implementation, but I do prefer this heap implementation because it's a lot more intuitive and it makes a lot more sense, right? So anyway, you'll have both the implementations down in the comments or in the description. You can just check them out. I hope you enjoyed this video. Hit the like button if you did, and subscribe to the channel for more videos, and I will see you in the next one.